Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 2, circles, chords, diameters, and their relationships. Okay, so here we go. Classwork opening exercise. Construct the perpendicular bisector of segment AB below as you did in Module 1. So this is a review, but I will do it. So here we go. So what you do is you put your compass stylus, the point at one end, open your compass more than halfway and let me change the color, and you draw an arc from A. Without changing the radius of your compass, you then put the compass at the end point B and you repeat the process. So there it is. Then you get a ruler and you connect where the two arcs intersect. So lining this up like so and drawing a line down through, and there is a perpendicular bisector. So this, what does that mean? Hello, didn't I just choose my pen? That means that this is 90 degrees, and if that is the point P right here, AP is congruent to BP. Okay. Draw another line that bisects AB, but is not perpendicular to it. You list one similarity and one difference between the two bisectors. Draw another line that bisects AB. Okay, so let me erase all of this here. Actually, I didn't want to erase that segment. So let me just put it back this way so it doesn't erase when I use my eraser. So if I go from here down to there, there is a perpendicular bisector. Now it says to construct another perpendicular bisector, actually another bisector, but that is not perpendicular. So all I have to do is take my ruler and line it up with that point that we called P that I erased. So that's point P right here. And I will draw a segment. So AP is still equal to BP going through this point right here. But this line here is not perpendicular to AB. List one similarity and one difference. Well, one similarity is it intersected AB at P, but one difference is the lines are not perpendicular. AB is not perpendicular to, if I called this C and D, I would say AB is not perpendicular to CD. Okay, so there's the difference. The similarity is it's still a bisector, so AP equals BP. Okay, page 2 brings us to exercise 1. Figures are not drawn to scale. Figures are not drawn at all. Prove the theorem. If a diameter of a circle bisects a chord, then it must be perpendicular to the chord. All right, so the first thing I'm going to do is construct a circle. So let me put a point here and we'll call it P. So it'll be circle P. And rather than just getting the circle tool, I will do this as if I were doing it on paper so you can follow along. And you take your compass and you put it on your point P, like so. You choose a radius, and I'm going to rotate this first. I want to make it kind of large so we can see. And so there is my circle P. Alrighty, so I constructed circle P. If the diameter of a circle bisects a chord. So the next thing we need to do is draw a chord. So a chord, by definition, is a line segment whose endpoints are on the circumference of the circle or the edge of the circle. So if I call this point A and this point B, and then got my ruler out, and it doesn't matter where you put it, just put it somewhere on the circle. As long as both points are right on the circle, then we're okay. And the chord does not continue through it, just the endpoints are on the circle. So this is chord AB. So I've drawn a circle and I've drawn a chord. Okay, and then so now I want to construct a perpendicular bisector of AB. So I get my compass. Let me rotate it so it's not off the screen. Okay, put the stylus on A. Let's change it to green. And remember how to do a perpendicular bisector. You want to open it up further than halfway. And then you draw an arc like so. Without changing the radius of the compass, you put the stylus on B and you repeat. So I'll bring this over here and it's going to intersect there. And just to make it neater, I'm not going to draw the full arc on this. So I'm just going to do that. I want to know where those two arcs intersect. Then I take my ruler and let's put that right on there and rotate so that we're right on there, and draw my segment. And actually I want it to be a diameter, so I'm going to go beyond. So let's just go beyond. So there we go. So AB is my chord. Okay, and the point going through P, this green one, that ends up being endpoints here. And here, if we didn't extend beyond, that would be a diameter because it's going through P. Okay, so what did we just do? Constructed a circle P, put a point here A, put another point here B, constructed a perpendicular bisector using my compass. So this point right here cuts the chord in half. So if this is Q, then I would say over here, the length of AQ equals the length of BQ. Okay? They're congruent because I formed a bisector. Well, what do you notice about this line we drew? Well, it's going through P, so therefore this is also a chord from, let's call this C and call this D. Segment CD is a chord, but it's also the diameter going through the center. So if I'm going to draw a perpendicular bisector to a chord, it will be perpendicular to the diameter. Okay, one other thing we want to say here is, one other thing I want to point out is if I then take my ruler and put it at P and rotate it, so I'm making a segment to B, I'll do it in purple. If I draw this segment to there, rotate this around to here and draw a segment from here to here, then those are both radii and therefore they are congruent. But they're not congruent to AQ, so let me do 2 marks. So AP is congruent to BP because they're both radii of the circle. And AQ is congruent to BQ. So AB is our chord. So it forms an isosceles triangle. So therefore this angle, angle PAQ, would be congruent to angle PBQ. So there's a whole bunch of stuff we can get from doing this perpendicular bisector. Okay, and then one last thing I would say is angle APB is a central angle. Okay, angle APB, if we have a vertex of an angle at the center of the circle, it's called a central angle. All right, number 2, prove the theorem. If a diameter of a circle is perpendicular to a chord, then it bisects the chord. Okay, it's a converse. Okay, so now we have to draw this up. We're going to write a proof. because it does say to prove the theorem. I just explained it with a diagram, but now I've got to back up that claim. So what I'm going to do is I'm going to draw an if-then statement table, like so. Okay, and then we're going to say this is statement, and this is reason. Okay, so what were we given? We have circle C. I'm sorry, circle P. I call it P. We have circle P, okay, with a diameter CD. Okay, we have a chord A, B. Okay. And a F, let's see, a Q. So it says if a diameter circle bisects a chord, then it must be perpendicular to the chord. So an if statement is a given. So we have the diameter of a circle bisecting a chord. So that means a Q is equal to BQ. Okay. I guess I don't need those lines over top, do I? Okay. So AQ equals the length of AQ equals the length of BQ. Those were all given. So I'll do given in black and then I'll switch to red. So what else were we given? What are we trying to prove? We're trying to prove that the diameter bisects the chord. I want to prove, so I'll write this up here. We want to prove CD is perpendicular to, I don't need the word is, CB is perpendicular to AB. Okay, that's what we're trying to prove. Segment CD is perpendicular to AB. Circle P with diameter CD, given. Chord AB, given. AQ equals BQ because the diameter is bisecting it. All givens. Now we're going to say, let's see. Okay, so we're going to use these two triangles. So I'm going to say QP, this segment here, QP, is in both triangles AQP and BQP. So I'm going to say QP equals QP. I'm sorry, AQ, I don't know what I'm doing here. I do know what I'm doing. I'm just AQ equals BQ. That is given. I've already written that. All right. And I do want to do that QP. I was on track. I'm just looking at my notes here. QP is equal to QP, and that's the reflexive property. Okay. QP is equal to itself. So I'll put a mark there. Okay. So now we are going to say that AP equals BP. Reason, radii of same circle are equal or congruent. They're equal in measure. Okay, so now I know this angle here is equal to this angle here. And we were already told that AQ equals BQ right here. Okay. And we just said that AP equals BP because they're both radii. So let's recap this. AQ equals BQ. That was given because it was bisecting the chord. QP is congruent to itself by the reflexive property. AP is congruent to BP because they're both radii of the circle. Now I can say triangle AQP is congruent to triangle BQP. And the reason, let me just move this up just a little. The reason for these two triangles congruent is S, S, S. Okay, now I can say the measure of angle AQP, the measure of angle AQP, AQP is right here, is going to equal the measure of angle BQP. BQP is right here. If the two triangles are congruent, then its corresponding parts are. So corresponding parts of, CPCTC, corresponding parts of congruent triangles are congruent. Okay? Now we can say angle AQP and angle BQP are right angles. So now we're going to say that these are right angles. And why is that? Equal angles, since they're equal because of corresponding parts of congruent triangles, if they are equal and they are a linear pair, that's 180 degrees, then they have to be 90 degrees. So that's what we would say. Equal angles that form a linear pair are 90 degrees. Okay, that's a straight line. If this angle equals that angle, half of 180 is 90. They both have to be 90. It's a must. So now I can say CD is perpendicular to AB. And that's just definition of perpendicular line. Okay, CD is perpendicular to AB because of those 90-degree angles. So once I can say that, well, that's it, we're done. We just proved CD is perpendicular to AB. So there is the two-part proof. Okay, so now we're going to do the converse in number 2. I don't want to scroll down any further because I want to use this circle in my next proof. So we use the same circle. But let me just get rid of, can't do it that way. Let me just clean this up and I get rid of those congruent markers. Okay, so here's the the diagram that we created. I took away all of the congruent symbols because we're going to do this again. This is a converse. So bring this in. So here's what we're given. Just to save some time, I'll put this right here. It says, prove the theorem if the diameter of a circle is perpendicular to a chord. So that's our given. We have a circle P, I'm going to call it P, not C, with the diameter, let's see, they're using different letters, so I'll just write this out. So what we're given is, given circle P with diameter CD, okay, chord AB, okay, and CD is is perpendicular to AB. Okay, if the diameter of a circle is perpendicular to the chord, that's a given. We have to prove it bisects. So we want to prove CD bisects AB. Okay, that's what we're trying to prove, that CD does in fact bisect CD. CD bisects AB. Okay, all right, so here we go. First thing I want to say is, here's our statement. And our reason. All right, let's use green this time. We were given CD perpendicular to AB. Okay. Angle, let's see, one moment here. Okay, so knowing that these are perpendicular, then I can say angle AQP and angle AQP and angle BQP, okay, AQP, BQP, they are right angles. Because CD is perpendicular to AB. So definition of perpendicular lines. Okay, so that just stated that that's 90 and that's 90. So now I can say triangle AQP and triangle BQP are right triangles. Okay. And that's just simply the definition of right triangles. Okay. If you've got a 90-degree angle in a triangle, it is a right triangle. And now I can say that angle AFC, angle AQP is congruent to angle BQP because right triangles are congruent. All right angles are congruent. Okay, if they're both 90 degrees, they're congruent. Agreed? Okay, so now I know I have an angle congruent to an angle. We're trying to prove AB is congruent to, or AQ is congruent to BQ because CD bisects it. So keep that in mind. So we have, now I want this side congruent to itself. So now I'm going to do QP is congruent to QP. That's a reflexive property. Okay, so now I have an angle and a side. Okay, and now I'm going to say AP is congruent to BP. So AP is congruent to BP. Reason, all radii in a circle are equal. And it's got to be the same circle, so I'll say that. All radii in the same circle are congruent. Okay. So now I have a side, I have a side, I have this angle. And remember, it's a right triangle. So this is the hypotenuse, and this is the leg. Keep in mind, you can't have ASS. Remember, in math, there is no formula for that, but in a right triangle, that's hypotenuse leg. So now I can say triangle AQP is congruent to triangle BQP. And the reason is hypotenuse leg. Okay, so now I can say AQ. Now I can say segment AQ is equal to BQ. Okay, AQ equals BQ. Because once we prove the triangles are congruent, then corresponding parts of congruent triangles are also congruent. Okay, and then what more do we need? We're trying to say that CD bisects AB. So that's what I'm going to say. So I've already said this, so now I can go right to it and say CD bisects AB. So CD is bisecting AB, and that's just simply, let me scroll a little here, the definition of segment bisector. All right. And we have proven that a diameter bisects a chord. So if a diameter is perpendicular to the chord, it bisects the chord. If a diameter of a circle bisects the chord, then it must be perpendicular. So we did the proof and we did the converse. Okay, page 3 brings us to number 3, another proof. Okay, the distance from the center of a circle to a chord. Well, just one moment there. Let's just be really clear about this. What are they talking about? The distance from, let's use a thin line. The distance from the center of a circle to a chord, which is right there. Let's just fix this a little and let's make it a little thicker. There. So that's what they're talking about. The distance from the center of a circle to a chord is defined as the length of the perpendicular segment from the center to that chord. So we just proved that if we drew a line from the center of a circle through a chord and was bisecting that chord, then it would be perpendicular. So the distance from the center of a circle to a chord is defined as the length of the perpendicular segment from the center to the chord. So that means that this is a right angle. Note that since this perpendicular segment may be extended to create a diameter, so I could extend this to here and then continue over to here, of the circle, the segment also bisects the chord. So then we also know that AF is congruent to BF. Okay, and it's proved in exercise 2. Now we want to prove the theorem in a circle, if two chords are congruent. So they're telling us that AB is congruent to CD, then the center is equidistant, meaning the same distance from those two chords. In other words, if I drew another segment here, and let's make this one orange. Aren't you glad I chose orange? Right there. So what they're saying is, prove that in a circle, if two chords, if AB is congruent to CD, then the center, O, is the same distance from F as it would be to E if CD is congruent to AB. And we're going to try to prove that. So here goes. So the first thing I want to state is what I just said in words. Okay, so we're given a circle O with a chord AB and a chord CD, and we're told AB equals CD because it says if two chords are congruent. So we're saying AB is congruent to CD. F is the midpoint of AB and E is the midpoint of CD because perpendiculars bisect. We want to prove OF is congruent to OE. Alrighty? Hopefully that's all clear to you now. So here we go. We're going to start this proof. So what are we going to say first? Well, we're going to do our givens. AB is equal to, so I don't need this bar above here. AB is equal to CD. Right here, given. So AB equals CD. Okay. And then we want to say that OF and OE are portions of a diameter. What does that mean? Well, if I took this E and dragged it further to there and extended this over to here, then now you can see that that would be a diameter. Okay, so OF and OE are portions of a diameter because they're going from a point through the center. And if you continue both directions, you'll get to the other side of the circle and they will be diameters. Okay, and that is the definition of diameter. Okay, so now I can say OF is perpendicular to AB. Okay, and OE is perpendicular to CD. And if the diameter of a circle bisects a chord, okay, then the diameter must be perpendicular to the chord. Okay, we just proved that in the previous page. So once we prove something, we can use it in our toolbox, if you will. So OF is perpendicular to AB and OE is perpendicular to CD. So therefore this is a right angle here as well. Okay, and now I can say angle AFO. So angle AFO and angle DEO, and that's a really bad %, and DEO. Yeah, let's move that. Angle DEO are right angles. And that's just definition of perpendicular lines. So if two lines are perpendicular, then obviously we are forming right angles. So I've got the wrong side labeled here, so let me fix that. Let's just label this side because that's what it said. AFO is and DEO are right angles. Definition of perpendicular lines. Okay, and if I form a triangle, so let's extend these like they said to do. There's a diameter. And then I extend this to the edge like so, through the center to the other end there like so. Okay, now you see that we have a triangle AFO. So now I can say triangle AFO and triangle CEO. Is that where I want it? I could also draw a segment here. It doesn't really matter, but now let me use orange. So this, whoops. Let me do a segment and let me keep it orange. So if I go over to here now what I'm doing here, I'm just, since we said D angle E is a 90-degree angle, I'm going to make a triangle over here. So it's triangle DEO. And that is also, DO is going to be congruent to CO because they're both radii. So now triangle ODE, or DEO, I mean, DEO. Switch back to blue. So triangle AFO and triangle DEO are right triangles. All right, so now I have two right triangles with the hypotenuse equal. And that's what we're leading up to, finding all this stuff. E and F are midpoints. So E, so now I'm going to say, let me extend this. Can't. So now we're going to say E is the midpoint of CD. And F is midpoint, the midpoint of AB. That's given. Okay, midpoints of AB and E is the midpoint of CD. F is the midpoint of AB. So now we're saying these, they are given. All right, so now that we know that that's the midpoint, what can we say about that? Now I can say AF, because we already said AB is equal to CD. And since these are midpoints, then the segments AF and ED or DE are equal. So AF equals DE. AF, let me erase this, by the way, it's hard to see with that right angle symbol, there's F. So AF equals DE because AB equals CD and F is a midpoint and E is a midpoint. So half of something that's equal to half of something else that's equal are equal. And AB, that's just midpoint rule. I'm just going to say midpoint. AB equals CD and F and E are midpoints of AB and CD. Okay. So now I'm going to say that AO equals DO. So the length of AO equals to the length of DO. Let me extend this. Okay. All right. Why is AO equal to DO? Radii of the same circle are equal. Okay, so now what do I have? Let me go back and label this now. So what did we say? AB, that's not part of our triangle, equals CD. But here we said E is the midpoint, so we said AF equals DE. So we said AF is congruent to DE. We just said OD is congruent to OA. So we also said that angle AFO and angle DEO are right triangles. So we have a right triangle and a right triangle, because that's the right angle there. And we have a leg, we have a hypotenuse. So now I can say the triangles. Triangle AFO is congruent to triangle DEO. The reason is HL. Okay, I've run out of room. Let me fix that. Okay, so what were we trying to prove? We're trying to prove OF is equal to OE. Well, here is OF and here is OE. It's the other leg of the triangles that are congruent. So now I can say OF equals OE. Reason? Corresponding parts of congruent triangles are congruent. Okay, and guess what? The proof is in the pudding. Alrighty then. Okay, page 4 brings us to number 4. Prove this theorem now. In a circle, circle O, if the center is equidistant from two chords, OF is equidistant. Okay, so O is AB, I should say, if the center is equidistant from two chords. So O is the same distance from AB as it is from CD. Then the two chords are congruent. Use the diagram below. So what are we given? Circle or O with chords A, B, and CD. And then we're given segment OF equal to OE, because it says right here, the two chords are, if in a circle, if the center is equidistant from two chords. So that's our if statement. So the center is the same distance from the chord. That means OF is the same distance as OE. That is our given. F is the midpoint of AB, then the two chords. If the center is equidistant from two chords, okay, if that's the case, then it's perpendicular, so it's got to hit at the center, perpendicular bisector. We proved that in this lesson. So F is the midpoint of AB, and E is the midpoint of CD. We want to prove, let's highlight this time. This is what we are trying to prove. AB equals CD. Now we're trying to prove the segments are congruent, the chords. So the first statement we're going to say is our given. OF equals OE. Reason, given. Okay, and I'm going to label my diagram. OF equals OE. All right, now we're going to say OF and OE are portions of diameters. And that's the definition of a diameter. Okay, now I'm going to say that OF is perpendicular to AB and OE is perpendicular to CD. Okay, so if the diameter, what am I writing? Whoops, thought I hit the eraser, missed. If the diameter of a circle bisects a chord, then it must be perpendicular. Okay. So now I can say angle AFO and angle DEO are right triangles. right angles. So AFO is right here. DEO is right here. So if the diameter of the circle bisects a chord, then it must be perpendicular. So if OF is perpendicular to AB, then it forms a right angle. If OE is perpendicular to CD, it forms a right angle. So therefore, angle AFO and DEO are right angles. Definition of a right angle. Okay. So, it's not definition of right angle, it's definition of, let me make this, perpendicular lines. Definition of perpendicular lines form right angles. All right. So now if I make a triangle, so let's switch to a segment. Let's draw it in here. Let's use red. So let's make a triangle here, triangle AFO and triangle DEO, like so. So now I can say triangle AFO and triangle DEO are right triangles. And that is definition of right triangle. Okay, so we have two right triangles. We know that we have an angle equal to an angle. We have a segment, a leg equal to a leg. And now I can say AO is congruent to DO. Radii of same circle are equal in measure. Okay. And now I can say triangle AFO is congruent to triangle DEO. Because this is congruent to this, OE is congruent to OF, and we have 90 degree, 90 degree. So that's hypotenuse leg. That's the reason for the congruence. Okay. Now that I've said that, I can now say the segment AF is equal to segment DE. The length of AF is equal to the length of DE, and that is corresponding parts of congruent triangles are congruent. All right, now we want to say this. Okay, so I'm not going to take the time to write that. F is midpoint of da 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 da. I'm just saving time here, and let me just extend this. So F is the midpoint of AB and E is the midpoint of CD. That is given. Okay. So that said, now we can say the whole thing since those are midpoints of that. Then now we can say AB equals CD. And that's what we were trying to prove right here. And the reason AF equals DE from here, okay? And F is midpoint of AB. E is midpoint of CD. And there you have it. Okie dokie. Okay, page 5, number 5. A central angle is defined by a chord. A central angle defined by a chord is an angle whose vertex is the center of the circle and whose rays intersect the circle. The point at which the angle's rays intersect the circle form the endpoints of the chord defined by the central angle. Prove the theorem. In a circle, circle O, congruent chords define central angles equal in measure. Use the diagram below. All right, so we're given that two chords are congruent. A central angle defined by a chord is an angle whose vertex is the center of the circle, whose rays intersect the point at which. Okay. Prove that in a circle, congruent chords define central angles equal in measure. So two chords are congruent. AB is congruent to CD. So we're going to say that AB is congruent to CD. Given. Okay, because it says in a circle, congruent chords define central angles equal in measure. Use the diagram below. Prove the theorem in a circle. If two chords define central angles equal in measure, then they are congruent. So first we want to say we're given that they're congruent. Proven the theorem in a circle, congruent chords define central angles equal in measure. So we're trying to prove central angles are equal in measure, given the fact that we have congruent chords. Okay, it's not really clear how they worded that, but that's what it is. All right, if we put it into an if-then statement, if is given, then is what we're trying to prove. So we're given AB is congruent to CD. I've labeled it, that is given. Okay, now I can say AO is congruent to DO. All radii in the same circle are equal in measure. Okay, so now I have this side is equal to this side is congruent to this side, and I can also say BO is congruent to CO. For the same reason as this. Okay, so now I can say triangle DOC is congruent to triangle AOB by side, side, side. Okay. And now I can say, so keep in mind, let me highlight these, by the way, the chords that we were given. Let's see, this, let's make it blue. We were given that AB and CD were the two chords, in fact, at the beginning. All right. So we have two triangles congruent. So now I can say that, what are we trying to prove? Central angles are equal in measure. And they gave the definition. So what that meant was central angles defined by a chord is an angle whose vertex is the center of the circle and whose rays intersect the circle. So angle AOB is right here. Okay, right there. Let me change that to green. Here's angle AOB. It's formed by OA and OB, which are congruent, and then it forms that arc. So now I can say angle AOB is congruent to angle DOC, AOB, DOC. Corresponding parts, congruent triangles are congruent. So there we just proved that the two central angles are equal in measure if the rays, in this case, radii, that go out to the edge of the circle that form the chords that are congruent, then the angles have to be congruent. So in other words, if AB is 6 and CD is 6, then the measure of angle DOC, which cuts that chord, and angle AOB, which cuts this chord, since the chords are congruent, the angles that form them must be congruent. Okay. Okay, so now number 6 says, prove. Let me see, am I recording? Yes. Prove in the theorem in a circle. We're going to use the same diagram, by the way, so let's just erase everything here. Now we're going to prove that in a circle of two chords define central angles equal in measure. So now we don't have the chords equal in measure. We have angles equal in measure. So we're given this angle equal to this angle. If two chords define central angles equal in measure, then they are congruent. So they want to prove the chords that define these angles. If the angles are congruent, the chords are congruent. So this is the converse of the previous. So the first thing I'm going to do is use the same exercise. And now we're given the measure of angle AOB is equal to the measure of angle DOC. And that is a given. We were told that if the angles are equal in measure, then they are congruent. So we want to prove the chords congruent. Okay, so there's step 1. The angles are congruent. Then the next thing I can say is, since already I have a circle are congruent, now I can say DO equals, or is congruent to AO, and CO is congruent to BO. All radii in the same circle are congruent, are equal in measure. Okay, so what does that mean? Well, let's label our diagram. So I said DO is equal to AO. CO is equal to BO. So there we have it. Well, we have enough now to say that triangle DOC is congruent to triangle AOB. Reason, side, angle, side. Once I say that, I can now say AB is congruent to CD. By corresponding parts of congruent triangles are congruent. And we have proved that if you have central angles congruent, then the chords they form will also be congruent. Okay. Okay, page 6 brings us to the end of lesson 2. Review the lesson summary and go to your problem set.